So in this video we're going to be looking at Kepler's laws of planetary motion. He has three laws. We're going to look at a derivation for a formula involving the period of an orbit, and we're going to do some calculations involving the stuff that we've been learning involving satellites. So he has three laws. The first law is simply that all planets move in elliptical orbits around the Sun at one focus. So technically, an ellipse is kind of like a circle but dragged out like an oval, and it's got two foci. Okay, foci is just the plural of focus. So the Sun, all planets move around the Sun in an elliptical orbit with the Sun at one of those foci. Now, so that's literally just the first law. All planets move in elliptical orbits with the Sun at one focus. Now, the second law is the following. So, the radius vector, so basically the line drawn from the Sun to a planet, sweeps out equal areas in equal amounts of time. So from C to D, that occurred, let's just say, over 3 months. And from B to A, that occurred over 3 months. And this line between the Sun and the planet sweeps out areas that are equal in equal time intervals. So even though, so obviously this area here is equal to this area here. So from C to D, this planet travelled much further than B to A. So what this means is Kepler's second law of planetary motion means that when a planet is closer to the Sun, that planet travels at a faster speed, because in order for this area to be equal to this area, obviously from A to B the planet was travelling much slower, because it's going to sweep out an area of the same amount. So if this was 3 months and this was 3 months, they're sweeping out the same sized area. So Kepler's second law of motion is that a vector drawn from the Sun to a planet sweeps out equal areas in equal amounts of time. Kepler's third law of motion is basically that the square of the period of an orbit, of a planet's orbit, is directly proportional to the radius cubed, to the cube of the radius. And this follows all planets. So if we plot the orbital period squared, so t squared on the x-axis, and then the mean radius of its orbit cubed, it's a directly proportional, so straight line through the origin. So there's a directly proportional relationship between the period squared and the mean radius of its orbit cubed. So all the planets in our solar system follow this. So orbital period squared is directly proportional to the mean radius cubed. And that's Kepler's third law of motion. And you need to be able to derive Kepler's third law of motion. So you need to be able to derive this one. So there's a few derivations. So the way that we derive this one is as follows. We know that we've derived this one previously. So the speed of a orbiting body is equal to the square root of the universal constant times by the mass of the central body divided by the radius. Okay, so that's the speed of, we look in terms of a satellite, but that's speed in terms of the planet orbiting the Sun. And now that speed, if something's undergoing uniform circular motion, it's going 2 pi r over t, because remember speed is distance over time. So it's 2 pi r over the period. So we can equate these two speeds. We can equate the speed, gm over r is equal to 2 pi r over t. We can then square both sides of the equation, and if we square this, we're going to be left with gm over r, and that's equal to 2 squared, which is 4, pi squared, which is pi squared, r squared, which is r squared, over t squared, or the period squared. And now we can simply rearrange this to get t squared on the left-hand side. So we're going to times both sides of the equation by t squared. And we had, so we're going to rearrange it. So if we times both sides of the equation by t squared, we'll get t squared on this side, and it will be cancelled out on that side. We can then also times, I might do this in steps, so we'll times both sides by t squared, and we'll times both sides of the equation by r. That'll cancel out, times this by r, so we'll be left with t squared gm equals 4 pi squared, and then r squared times r is r to the power of 3. And then finally we'll divide both sides by gm, and we'll be left with the period squared is equal to 4 pi squared divided by gm r cubed. So you need to be able to do that derivation, just equating both of these on your formula sheet. This speed is on your formula sheet, this speed is on your formula sheet. And then just rearranging them so that we finally get the period squared as the subject of our rearrangement. Now, we're going to do a couple examples where we do some calculations. So, a satellite circles the Earth over its equator once every 12 hours. Now, the mass of the Earth and the radius of the Earth are on your formula sheet. So, have your formula sheet out ready. Don't need to memorize these numbers or anything, but they'll be on your formula sheet. So, part A, calculate the period of the satellite in seconds. So, period of a satellite, we would use this one generally. We're given the period of the satellite because it tells us that the satellite circles the Earth over its equator once every 12 hours. So it circles around every 12 hours, completes an orbit in 12 hours. So part A, we want it in seconds. So we want to go from 12 hours into seconds. So 12 hours is going to be 60 minutes, and then each minute will have 60 seconds. So if we use our calculator, we'll get, if we write it to 3 significant figures in scientific notation, let me just find my calculator. Twelve times 60 is 43,200 seconds. And we want to start getting in the habit of writing things to 3 significant figures in scientific notation. So we move to decimal place once, twice, 3, 4 times. So it'll be 4.32 times 10 to the 1, 2, 4 seconds. A lot of seconds. Now, part B. Calculate the satellite's height above the Earth. So to find the satellite's height, we're obviously going to need, if we have the Earth and we have the satellite, we want to find this distance. We're going to first need to find the radius in order to find the height. So to find the radius, which equation are we going to use? Well, we could use multiple, they all have radius in it. Now, what do we know? We only know the period, so we know T is what we know. We know the mass of the Earth, the big central body. So, could we use this? We don't know the speed, no, so we can't. Can we want to get the radius, can we use this one? This one has period, which we know, G, which is a constant, big M, which is the mass of the central body. In this case, it's the mass of the Earth. So we can use this equation. So we've got T squared equals 4 pi squared over GM R cubed. Now we want to rearrange this equation for radius. So what we can do is we can times both sides by G and M. So we'll have radius cubed equals period squared times G times M. And then to get rid of 4 pi squared, we can divide both sides of the equation by 4 pi squared. And then finally, this isn't squared now, this is cubed. So the opposite of cubing something is cube rooting something. And there is a cube root button on your calculator. If you don't know where it is, I can show you where it is. Just see me. So the opposite of cubing something is cube rooting it. So if we substitute in our numbers, so period squared, period has to be in seconds. So it'll be 4.32 times 10 to the 4 times by the universal constant, which is 6.67 times 10 to the negative 11 times by the mass of the Earth, which is 5. Oops, not sure what happened to my pen. 5.97 times 10 to the 24, and we're going to divide that by 4 pi squared. And then we're going to cube root it, and if you type that into your calculator correctly, you should get, I better do it. (4.32x4) times by 6.67x to the negative 11 times by 5.97x to the 24 divided by 4 pi squared, and then the cube root of my answer, and I get let me pause and redo it. I think that should be fine. So of course what I forgot to do is, and if I go back, I forgot to square it because it's period squared. I missed the squared. Oops, I don't know why it deleted some of what I wrote down. So the mass of the Earth is 5.97 times 10, and my pen has just lost it. Divide by 4 pi squared. And that is equal to, and if you type it in correctly, it's 2.66 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7, that's meters. So that's how far the radius is from the center of the Earth up to the satellite. Now that's not what we actually wanted to find, we wanted to find the height above the Earth. So now to find the height, we had to do the 2.66 times 10 to the 7, subtract the radius of the Earth, which is 6.38 times 10 to the 6. And if we do that calculation, we'll get 2.02 times 10 to the 7 meters. So it's still a huge height above the Earth. Now part C. In part C, we want to find the speed of the satellite. So, speed of the satellite, we can simply just use either of these two. So we're going to do that the speed is equal to the square root of the universal constant times by the mass of the Earth divided by the radius at which it's travelling at. So if we substitute in our unknown numbers, we know that universal constant is 6.67 times 10 to the negative 11. We know the mass of the Earth, etc., etc. I don't have enough room, but if we type that into our calculator, we'll get the speed of the satellite is moving at 3.87 times 10 to the 3 meters per second. Now, our second example that we're going to go through. So a large Earth satellite has a mass of 2 times 10 to the 3 kilos, so 2 ton, orbits the Earth in a circular path with a speed of 5.9 times 10 to the 3. Similar in speed to the previous one. So, calculate the radius of orbit for this satellite. So we've got mass, we've got speed, and we want radius. So we can either use this one, nope, because we don't have period. So we can use calculate the radius. So can we use this one? Nope, we don't have period. So we're going to have to use this one because it has radius. We know the mass of the Earth from the previous slide. The mass of the Earth was, what was the mass of the Earth? The mass of the Earth was 5.97 times 10 to the 24 kilos. So we know the mass of the Earth, we know the universal constant. Universal constant is 6.67 times 10 to the minus 11. And we know the speed. So in part A, we're going to rearrange the equation. So we're going to rearrange this equation for r, because we want the radius. So first things first is, in order to get to r, we need to square both sides of the equation. So we'll have v squared equals gm over r. So we've removed the square root. Now to get r by itself, we're going to times r by both sides, and then we're going to divide v squared for both sides. So these are just going to swap positions. So we get the radius is equal to gm over speed squared. And then substituting in, we get 6.67 times 10 to the minus 11 times by the mass of the Earth, which is 5.97 times 10 to the 24, divided by speed squared. I'm not missing the square this time, so the speed was 5.9 times 10 to the 3 squared. And if we type that into our calculator, we'll get that the radius is approximately, well, is 1.14, rounded to three significant figures, 1.14 times 10 to the 7, and that's in meters. So part B, calculate the period for this satellite. So this is our equation for period, but a simpler one rather than this one. Well, we do have the radius, but this one's a bit more complicated. We can simply use this one because we have the speed of the satellite. We have the radius of the orbit now. So we could use either of them. Oh no, we can't use either of them. No, we could use either of them. Either this or this. This one's a little bit easier to rearrange for me. So to rearrange this one, we're just going to swap these positions. So the period will simply be 2 pi r divided by its speed. So it'll be 2 times pi times the radius, which we just calculated, over the speed, which we got given. And if we type that into our calculator, we'll get a period of 1.21 times 10 to the 4 seconds. Part C. Calculate the magnitude and direction of the force acting on the satellite. Well, in order for the satellite to be orbiting the Earth, it needs to be undergoing uniform circular motion. So we know that force is equal to mass times acceleration. If it's undergoing uniform circular motion, it's undergoing centripetal acceleration. And we know that centripetal acceleration is v squared over r. So the force causing this centripetal acceleration is going to be mv squared over r. We have the mass of the satellite, we have the speed it's traveling at, and we have its radius. So we can substitute that in. So the mass of the satellite is 2 times 10 to the 3. The speed it's traveling at is 5.9 times 10 to the 3. And then we need to square that speed over the radius, and the radius of the orbit of that satellite is what we calculated in part A. That is 1.14 times 10 to the 7 meters. So we can now type that into our calculator, and we'll get that the force is 6.11 to three significant figures times 10 to the 3. And because it's a force, it's in newtons, and it asks for the direction. So force acting on the satellite is towards the center of its path, which is towards the center of Earth. So Name the force that provides a centripetal acceleration in this example. So in this example, the force is a gravitational force. That gravitational force that's causing this satellite to undergo uniform circular motion. So now we can have a go at the rest of the questions in gravitation. They'll be on the Google Slides sheets. Cheers.